Hello, this video presentation is on fractional exponents. Our exponents up until this point have only been integers, positive or negative, but there's been no fractions. Fractions help us a lot. How would we multiply the square root of 5 times the cube root of 7? We don't have any way to write that. There's no possible way that we could express this product. With fractional exponents, we can very easily. So, in general, the most important thing from this video is that when we have a base, I'll call it b, raised to the p over, normally I write q, but I'm going to do r, p over r, raised to that power, that means b to the p power, that we take the, what we say, the rth root of that. The numerator is the power, the denominator is the root. We can also write this as the rth root of b all to the p power. Generally, this is preferable. Reason being is it's a lot easier to take the root of a smaller number and then raise it to a power than the other way around. And we'll look at an example in a minute. Now, this is called exponential form. This is the exponential form. Exponential. And this is radical form. And you're going to be asked to put things in one or the other. So let's look at a couple of quick examples. 8 raised to the 5/3 power. That means the bottom is the root. We're taking the cube root of 8 to the 5th power. I have no idea what 8 to the 5th power is. I'm afraid to even multiply that out. I'm not going to try to figure that out. Instead, I'm going to take the cube root of 8 and then I'm going to raise that to the 5th power. Well, the cube root of 8 we should know is 2. 2 to the 5th power is 2 times 4, 16, 32. It's 32. So that's what I was talking about before. It's easier to use this form. Much easier. All right, let's look at another example. The 16 to the 1/4 power. That is the 4th root of 16, and 16, 2 goes in there, 8, 4, 2 and 2. There's 4 2's. The 4th root of 16 is 2. One more quick example. We'll have 27/8 since I'm taking the whole fraction to a power, we'll put this at the 4/3 power. So that is the cube root of 27 over the cube root of 8. I look at the numerator and denominator separately, and then that's all raised to the 4th power. Well, the cube root of 27 is 3, the cube root of 8 is 2, raised to the 4th power, and 3 times 3 is 9, 9 times 9 is 81, 3 to the 4th power is 81, and we already looked at 2 to the 4th power is 16. Now, doing this, putting it in this form, has no benefit so far, because what I'm doing is putting it in the form we used prior. But now let's look at something else. There's also advantages when solving equations, which we'll look at next, not today. But if I have the cube root, let's look at the example I did before. Oh, I erased it. So I'm going to take the cube root of 4 times the square root of 8. Well, the cube root of 4 is 4 cube root of 4 is 4 to the 1/3 power. And the square root of 8, and this is important, I should have mentioned it earlier, square root of 8 is 8 to the 1/2. We never put a 2 in here, but with the square root, it's just like having a 2. All right? But we never write it in there. Don't ever do it. Now, here we're multiplying, but they're not like bases. But I can do it. I can change 4 to 2 squared to the 1/3. And I can change 8 to 2 cubed to the 1/2. And when we take a power to a power, we multiply the exponents. So that's 2 to the 2/3 power. This is 2 to the 3/2 power. And lastly, when we multiply like bases, we add the exponents. So I have 2 to the 2/3 plus 3/2 power. In order to add fractions, I need a common denominator, multiply by 3 over 3, 2 over 2, and I end up with 2 to, this is 4/6 plus 9/6, 13/6, 2 to the 13/6 power in exponential form. Now, taking this original problem, I would have had no way of doing this prior to this. Now, the only thing here that's a little bit confusing is you have to write this with like bases. All right? If it's not like bases, it still won't work. As long as the bases can be expressed with the same base, we're good to go. All right, we'll look at another example of this later, but this is one big advantage of having fractional exponents. All right, have a great day, have a great weekend, and I'll talk to you later. See ya.